Hello, my name is Braden, and today I'm going to teach you about the concept of something called tributary area and how it's used to design beams in structural engineering. Now, let's consider something we're all familiar with, this house. It's got walls on all four sides, they're all 20 feet in length, and it's got a big roof on top. Now, there's one thing you need to know about structural engineering. Everything in the structure has a weight, or as we like to call it, a load, and that load has to safely make it down to the ground without anything breaking along the way. Now, the big load in this house is coming from the roof. It's applying a surface pressure in this plane just above the walls, and it's acting down on the walls. You can think of this as a big mattress sitting on top of the walls. Now, as I said, it's my job to make sure that this load makes it safely down to the ground. And right now, the only thing trying to hold all of this surface pressure are the walls on the sides. But this pressure is too big. If we left it this way, instead of our house looking something like this, a roof that's sitting straight, it would look something more like this. Our roof would start falling down to the house below. So why is it failing? Well, the distance between these two walls is too great, and our pressure is too large. If you imagine the walls having arms, they just can't reach far enough out in the pressure zone to hold it all up. They need help, a partner to help them carry the load. Enter the beam. Now, we can install the beam right here in the center of the house. And we'll put this pressure right back on top. Now, the beam is there to help us carry some of that pressure. But as a structural engineer, I need to be able to say with confidence what size beam this should be. That means I need to figure out exactly how much of this pressure is acting on the beam below it and how much is going to the walls. That's where the concept of tributary area comes in. The tributary area is a way for us to determine how much of the pressure the beam is holding up. And you can see this visually here. The tributary area of this beam is represented by what's in green. It's the area that the beam is holding up. Now, a good way to remember this concept is to remember that tributary area is a contribution. The beam is contributing to the overall structure by holding up his share of the area while the walls hold up their share. Now, let's dive a little deeper into this. We can see this more clearly by looking at our pressure from the top. This is the pressure of our roof acting down, viewed from the top. You can see that our dimensions are still the same, 2 feet, 20 feet by 20 feet, and our beam is right here in the center. Now, how do we determine the exact size of that tributary area? Well, we first say where we want the beam, in this case the center, and then we pretend the beam is reaching out to the walls on its left and right, and the beam says, "Hey guys, I tell you what, I'll meet you halfway." So what we do is we measure half the distance to the next support on one side and then half the distance to the next support on the other side. So in this case, there's 10 feet to the next wall, halfway would be 5. And then in this side, there's 10 feet to the next wall, halfway would be 5. So there's 5 here, 5 here. So the tributary area will be 10 feet in width. We can see that here, our beam resting on top. Now, what happens if we move our beam? Well, let's see. If we shift our beam to, let's say, 4 feet from this left wall, then the concept still applies. We reach out to the wall on its left and say, "Hey, I'll meet you halfway." That distance is 4 feet, halfway is 2 feet. The distance here to the next wall is 16 feet, halfway would be 8 feet. So 2 feet here, 8 feet there, that's still 10 feet. So our tributary area won't change. The only thing that will change is the contribution of the walls on the sides. You can see here, since we shifted our tributary area that way, the contribution of this wall has gotten greater, while this one has gotten less. Now, we want to make it even. We want to make it fair to the walls, so we'll keep our tributary area in the center, which means we'll install our beam in the center. Okay, so how do we use this to determine the size of the beam? Well, in structural engineering, we design our beams using a 2D analysis. We model the length of our beam and apply a linear load on it to determine what kind of reactions the beam is going to have. So we need a way to convert this tributary area into a linear load. Let's see how. Let's look at our pressures from a different perspective. We've got our beam here, and then we've got that surface pressure of the roof above. Now we're viewing this from a top angle, similar to how it was in the beginning. You can see here that our pressure is 20 feet by 20 feet, and each of these squares represents a foot in length. Okay? Now the pressure from our roof is exactly 50 pounds per square foot, or 50 pounds of force per square feet. And that 50 pounds is represented by each of these little arrows. Each of these squares is a foot by a foot, so they're a square foot, and each of these arrows is 50 pounds of force acting down on it. So the arrows here all represent individual 50-pound forces. So let's put our tributary area on top. Now, as we learned, the length of our tributary area is 10 feet. In order to determine the linear load on the beam, all we have to do is somehow get all of the pressure acting in this area into a linear load along the beam. And what we can do is we can compress this pressure until we get it into a line that aligns perfectly along our beam. So in each foot, we'll take these arrows and compress it. And you can see here, each foot is represented by the square. So in each line here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 arrows. So if we compress it, that means within each foot, we'll have 10 arrows acting down. Now, if each arrow is 50 pounds force, we have 10 arrows. That should be 500 pounds acting along each foot along the beam. Now, let's look at that mathematically. Our linear load is given by W here. We have our pressure, 50-pound force per square foot, times our tributary width, and we multiply these two together. And what happens is the foot here cancels with the foot there, and we're left with pound force over foot. And if you multiply the 50 and the 10, you have 500 pound force per linear foot. And that's represented by this here. Now, as I said, we compressed those arrows together into a linear load acting along the beam. And you can see here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 arrows acting down on the beam along each foot, or 500 pounds per linear foot. Now, all we have to do is take that linear load and apply it to our beam model. And from there, we can determine how the beam reacts and determine exactly what size our beam should be. All right, guys, I hope you enjoyed it. Thanks for watching.